Dear students, in continuation to the last two lectures, we are starting now the symmetrical fault analysis. Up to the previous two lectures, we have studied the basic concept regarding the per unit system and uh, single phase representation of balanced three phase system. Now, after the basic concepts, we are dealing with the fault analysis. First, we will discuss about the symmetrical fault analysis, and later on we will discuss about the unsymmetrical fault analysis. As we have discussed that a fault involving all the three phases is known as the symmetrical fault, while one involving one or two phases is known as the unsymmetrical fault. For example, single line to ground fault, line to line fault, two line to ground fault. These are the unsymmetrical fault, while where the three phases are involved, then it is a symmetrical fault. Majority of faults are unsymmetrical fault. Maximum 90% fault are the unsymmetrical one. There is a rare chance that the fault will occur in all the three phases simultaneously. So it is important to determine the values of system voltage and current during fault condition so that the protective device may be set to detect the fault and isolate the faulty portion of the system so as to minimize the harmful effect of such contingencies. What is the need of fault analysis? Fault analysis is needed to design the protection system. If we don't know the effect of fault, the severity of fault, how much current will flow, if a particular type of fault will occur, then how we decide the rating of the protection system. So to design the protection system, it is very important to calculate the fault current and fault parameters. So first we will discuss the symmetrical fault. One thing is that as we use the fault analysis to design the protection system, so there is the accuracy or precisionness is not important parameter to calculate the fault parameter, fault current or fault voltage, because we have to use this data for the designing of the protection system. Suppose in the calculation we have to calculate the fault current is occur 1509 ohm. Then when we design the protection system, we take the our circuit breaker or relay for up to the level of 1506 or 1600 ohm. So there is not a problem of 1 or 2 ampere. So we may take some consideration regarding them for the calculation purpose. So first, the symmetrical fault. Circuit breaker MVA breaking capacity was based on the three-phase fault MVA. High precision is not necessary when calculating the three-phase fault level, as I discussed. Following assumption is made in fault calculation. We have to calculate. We have to take some assumption for the calculation purpose. The EMF of all generator are 1 angle 0 per unit. This means that system voltage is at its nominal value and the system is operating on no load at the time of the fault. As we discussed that we have no need of precision data, high precision data, so we may assume the EMF of all generator are 1 angle 0 per unit. Shunt capacitance are neglected and shunt resistance is also neglected. Only inductive reactance of the system is taken into the step. Very simple assumption are there. We have to calculate, we have to make the voltage level of all generator 1 angle 0, and we only select the inductive reactance of the system, and we have neglect the resistive or capacitive reactances. So what is the steps? to calculate the fault current, suppose a numerical problem is given to you. There is a language form in which we can say that a generator is connected to a transmission line connected to the P1, P2, and so on. So a numerical can be in the language form. So first step, draw a single line diagram of the system. Means we have to pictorially represent the diagram of our system and take the ratings of these components, all the components of the system. Then I have already discussed to you when I have discussed the per unit system. To solve the three symmetrical fault, we have to make the system per unit system diagram. So then select a common base, find out the per unit reactance of the all generator, transmission line, etc. All the parameters, all the components. We have to choose the per unit value. From the single line diagram, draw a single line reactance diagram. Means we have to write the reactances of the all the components. Then reduce the reactance diagram by series, parallel, and star delta transformer, keeping the identity of the fault point intact. Means as in the previous example which we will discuss in the previous class, this is the fault point F. So this point F should be intact, means it should not be missing, and by keeping this point intact we may do some calculation. Suppose these reactances, these four reactances are series, then we can make a series combination of them. These two reactances are in parallel, and the generator G1 or G2 may be uh, outside of this because the rating are same 1 angle 0, so we can distribute it outside from this system as a 1 angle 0 single generator. So source redistribution may be performed here, and we can say that these are in the parallel. Then the parallel combination of this and this will become in a equivalent impedance, and we can calculate the current in that line. So we can it depends upon the network. So according to the network, as we have studied in the circuit analysis, we can solve the circuit by different method, either series parallel combination or star delta transformation or any other method. We can solve the circuit, but it should be noted that the fault point where we calculate the fault current or other parameter, it should be intact, it should not be missing. So this is the very simple steps to solve the fault current. We solve the symmetrical to find the symmetrical fault current. We can easily understand this thing by very simple numerical, by a numerical example. This is a system. There is G1, G2 are the generator, transformer T1, transformer T2. Then this is a line. Then there are two lines, 0.2 ohm per phase per kilometer, and this is the fault point F. We have to calculate the fault current, symmetrical fault current in the system. Basically, this is a three-phase system, but we have make a single phase representation of the system. So we have to calculate the current at this point. Then the first step, according to our steps, we have to make the EMF of all the generator is 1 angle 0, and we have to calculate the impedances of all the components in our own system according to the base value selected. So I am not discussing that one. So one page is missing here, but I will not discussing that part. We have to convert this system into the per unit system. We have to make the values of these all the parameters calculate again as our own system. We have to suppose we choose 100 MVA as a base, then the voltage level is 11 kV, and 11 kV is converted into the 132 kV. So the base value of voltage up to the primary is 11, up to the secondary it is 132 kV, and whole the system it will become 132 kV system. So the values, as we recalculate, we can redraw the diagram. This is one angle 0, one angle 0, and the impedances are shown here. Transformer is replaced by the impedances, then G2, and then there is the impedance of G2 and transformer T2 impedance. Then there is a line. Then again there is a two impedances and which are in parallel, and this is the fault point F. So if we want to solve it, then if the value of G1 and G2 will be same, we can also that this is a grounded. So G1 and G2 terminal is also grounded. So it will become the complete whole circuit, and we can make the G1 and G2 outside that circuit, because if the value of source is same, the source can be redistributed according to circuit analysis concept. So G1 and G2 become outside as a single generator, one angle 0, and this system will become in parallel. So the impedances of G2 and impedances of transformer T2 are in series. There is a series combination. There is a series combination, and the equivalent of these series combination and equivalent of G2 series combination, then these two are come in the parallel. Similarly, these two are in the parallel. So the equivalent value of this parallel combination and this parallel combination, this will become as a series combination. So equivalent impedances of the whole system, whole the network can be calculated. Then the current in the fault point F is simple as I is equals to V upon A. V is the one angle 0 divided by the whole impedances of the system. So actually this thing is missing. One page is missing for scanning it, but I have explained you. I have discussed this thing to you. Now another question is asked here. What is the if suppose we calculate the total fault current, then what is the contribution of G1 and what is the contribution of G2? Then if we know that there is a fault current F, and this will suppose the current G1 is supplied I1, G2 is supplied I2, and total current is I, then we can distribute the current in the I1, I2 by the formula I1 is equals to R2 upon R1 plus R2 total current I. Similarly, I2 is equals to R1 upon R1 plus R2 divided by multiply by the I. So by this concept we can divide the current G1 and G2. This is the division of current. This is the total fault current J 0.36, and this is the this is the R1. This is R1 plus R2, and this is 1995 point angle minus 90 is the total fault current. So this can be divided, and before producing the actual result we have to multiply it to the base current. So base current can be calculated. I base is equals to 100 MVA into MVA due to the M is 1000, and kV 11 kV, so root 3 into 11. So this is the base current at this point. So when this base current can be calculated, we have to multiply the base current to the faulted current in the per unit, which we occur is here 5248.8. This is the base current, this is the per unit current. So this is the actual fault current, this is the value of actual fault current. And one more thing is calculated is a fault MVA or fault level. Fault level is nothing but the fault current into base MVA. This is called as a fault level. So this thing is calculated in this numerical. So thank you for listening it.